Hi, this is Physics 2212. I'm Ali Panjani. Let's go through Lab 4. Introduction. The objectives are to predict how the circuits or reactors in a series will behave. Analyze the behavior of ohmic resistors and capacitors using FET simulation. Measure experimental values of current and voltage using different millimeters. Compare the experimental results with the theoretical calculations. Key findings. The current in resistor 2 has a circuit what zero point zero 0.02 amps. This was calculated using values for current and voltage which were consistent. A higher resistance in the RC circuit leads to a stronger charge and discharge for different times, and the ch time was almost 6 seconds. Key concepts: the node rule, I in equals I out, and the loop rule. The total voltage change in the closed loop. The rule is based on the principle of conservation of energy. The round trip would be 0. Electrical resistance R. The equation usually is R equals V divided by I, the resistance of any component, followed by Ohm's law, assuming the resistance remains constant. Equivalent resistance in parallel circuits. Whenever a resistor are connected in parallel, the total equivalent resistance is found using the formula. 1 over R equivalent equals the sum of 1 over the other. Uh, equivalent resistance in series circuit. When the resistors are connected in a series, the total equivalent resistance is simply the sum of all individual resistance. Capacitance is another key concept. It measures how much electric charge a capacitor can store for each output unit of potential voltage. It is defined as a charge Q on the plate divided by the absolute value of the potential difference. The capacitance can also be expressed as a product of vacuum per, permittivity and the plate area divided by the separation distance. These are the visual models. System ammeters or voltmeters. The surroundings are circuits. Initial circuit, simple circuit. The FET simulation. Build a circuit that includes two batteries, two resistors, two ammeters. The result, 0.0204 ammeters. Actual current, 0.02 ammeters. Reverse ammeter reading, negative 0.02 ammeters. Open circuit. Predicted values over its potential difference is 3 volts. A current is 0 amps, and the potential difference 3 volts, and the current is 0 amps. Managing potential difference around the circuit. A to B is 3 volts, B to C is 0, C to D is negative 0.96 volts, D to E is 0 volts, E to F is negative 2.04 volts, F to G is 0 volts, G to H is 0 volts, H to A is 0 volts. Findings in loop rule. The measurements supports the loop rule, which states the total voltage in the closed loop. 3 volts minus 0.96 volts minus 2.04 volts equals 0 volts. Ammeters in parallel. Circuit modifications. Configure the circuit so that an ammeter is placed in the parallel with a 100 ohm resistor. The current increases from 0.02 amps to 0.06 amps. The verification mathematical calculations can be used to confirm these findings. Calculating resistance. Calculating resistance using experimental values. Determine the resistance of resistors, the ammeter, and the wire using experimental data. R equals V divided by R. I. The experimental resistance values. 47 ohm resistor, 48 ohms. 100 ohm resistor, 102 ohm. Ammeter resistance, 0 ohms. Wire resistance, 0 ohms. RC circuit. Components used. 10 ohm resistor, 200 MF capacitor, 9V battery, and then measurement progress. To take it at the capacitor at a time and place. of discharge, repeating with a 20 ohm resistor. The results are for the 10 ohm resistor is a charging time of 15.4 seconds, discharge time of 15.2 seconds. The ohm resistor, 20 ohms, charging time 25.9 ohm, discharge time 27.5 ohm. Include key conclusion: higher resistance leads to a longer time for charge movement. This time dependent components used 9V battery, 30 ohm resistor, 2000 mF capacitor. The previous listed there. The plot versus time. V is potential difference. VO is initial potential. Discussion. The discrepancy is due to emitter precision. The emitter only measures the hundredth place, making it less precise. When you're measuring to the tens of hundredth place of the calculated value, the resistance becomes more accurate and better aligned. Uh, Potential sources of error: the emitter precision, the rounding error, the timing inaccuracies, the difference in real life circuits. What if scenario one using a real ammeter has a non-zero resistance even if it's small. The wires have some resistance, but is usually ignored in ideal models. This would cause a slight decrease in the current, lowering the reading of the ammeter due to resistance. In scenario two, the ideal predicts the capacitor of the fully charged almost within 1 second. In reality, this would not happen because the wires have resistance and slowing the charge. The capacitor itself would have internal resistance. Thank you. That's my TED Talk.